It's my pleasure to be able to introduce the program for today. This is the Fred Whipple Award and Lecture of the Planetary Sciences section of the AGU. Our speaker, of course, as you all know, is Jean-Pierre Bibring. I want to just say a couple of words and then turn it over to Jean-Pierre. The award is named after Fred Whipple. Many of you will remember him or certainly be familiar with his work. And in trying to think of how I wanted to compare Jean-Pierre to Fred, I think the approach that I'm going to take is that if you remember back to Fred's work on comets, the significance was in overturning the existing paradigm and setting the paradigm for the future. It happens in his case that the paradigm has stood for 60 or 70 years. With Jean-Pierre, we've watched him set up the paradigm for Mars, overturning some of the previous ones, and we will see if this one lasts 60 or 70 years. It's a little early to say. I looked at Jean-Pierre's CV to try to figure out what I could say that would be most appropriate. The thing that took me most by surprise, knowing his background and experience with hyperspectral remote imaging of Mars, the thing that took me most by surprise was that his PhD was on solar wind implantation into the lunar regolith. That suggests a tremendously broad capability and expertise, and one that I hope we'll be able to take advantage of in the future. I'm not going to list the missions he's involved with or the awards he's received because I want to leave some time for him to speak. The work that he's most known for today involves the Omega instrument and detection of hydrated sulfates and phyllosilicates on Mars, and putting the history of the mineralogy into a time scale that is currently driving our understanding of Mars, our investigation into the future. But the last thing before I turn it over to Jean-Pierre, I have a certificate that I'd like to present to him. This is for the 2009 Whipple Award presented to Jean-Pierre Bibring for outstanding contributions to the field of planetary sciences. And you can't see it, Jean-Pierre, but there's another one behind here that is a certificate for giving the lecture. So you get one for the award and one for the lecture. So congratulations, Jean-Pierre, and thank you. And without further ado, I will turn it over to Jean-Pierre.
Many thanks, Bruce. It's there are very few moments in one's life, research life, like these moments we are living now. I mean, every day is tough, but these moments are really delicious. And okay, it's very difficult in a language is not ours to translate the feeling that might have at these moments, but they are very, very deep, really. And it's more than an honor. I never thought that one day I would be present with you, who are I think I have prepared one or two slides just to say, well, this community here is really the one who has translated the view of the solar system that was essentially points on telescopes not resolved into something that 20 years later has really make a revolution there. And that's really this community here. And to be honored by this community as someone who might have contributed to and belonging to the same family is really something that I could not express and translate more than what I'm trying to do now. Many, many thanks, really. And what I'm trying to say now is really to put the scope of what we have been doing over the past years in the frame that I have personally, thanks to all what has been done on this continent here, that the fact that planets after planets, we discovered that really, although they were thought long ago as really generic things, essentially equal, they have a striking diversity. And at the same time, we have understood that they come from a single origin, really. And so there is what I say a dialectic contrast between the two here that we are very far from having understood really. What drives the evolution of the planet is not trivial here. And again, it's not only a matter of curiosity, but we need to know why the Earth is so different, so specific. And there is an urgent need, of course, to do so, as I say here, and what happens in Copenhagen really demonstrate that the subtle processes in place here to understand how the planet works have to be understood on a very small timescale now. The point I would like to make here tonight is to say, well, that the Mars exploration has to do with that. And Mars is really unique to tell us a lot of things that we are trying to understand for our own planet. And I will essentially illustrate these now in a few things. The reason why, of course, everyone here in the room knows the reason why Mars is so important. It's essentially a matter not only the distance from the Sun, but the size. It's large enough as compared to the Moon, of course, to have undergone a lot of activity here, but it's small enough not to have erased that by global resetting all of the time as the Earth did. And so in principle, potentially, if you are clever enough, you can read on Mars essentially all the steps and processes that through which all the inner planets have gone through. So what is really new, and maybe some of you will not accept that, but I think that what is really new over the past 5-6 years is really that we have been able now to systematically couple imagery to composition. And that's what I'm trying to express here. Of course, it's not to say that everything goes from this coupling. Lots of things has been done independently of that. But this coupling has been tremendously efficient, and the potential is huge. Near-infrared spectrometry is one of the tools, not the single one, of course, and the fact that we have on the ground the possibility to measure what we see from space, of course, is a major component of that. But it's really what we do here, and I will express my deep regards to, of course, those who made that possible on ESA side with the Mars Express and on the NASA side with MRO with the CRISM instrument on board. And so what I will essentially in a few minutes now is concentrate on only a few points here that I think, to my prospect, have been the most important over what we have found now. And I will go from the present state to the old times to try to convince you that at all time scales, what we learn from Mars is important for the Earth also. I will start with something which is rather new now, although it's not really done over the past weeks, but it's over the past months, is the question of the Mars clouds. And the reason why I'm putting that here is that, of course, on the other side of the Atlantic now, we're discussing the possibility for the clouds to control the evolution of the global scale climatic change that we face on the Earth here. And so the question is how the clouds form, and something that has been done in our institute, in particular under Brigitte Gondet. What Omega has done, and then CRISM, of course, is to confirm that most of the clouds which have been seen for years by a number of means are really H2O clouds. But what is new, really, that we have found that we have a high altitude, what we call the mesospheric clouds, which are 80 kilometers in altitude, and these are absolutely fundamental in a sense, because they were not suspected, and the nucleation of these are really very specific. Just one diagram to express to you that the reason, if we have such a high altitude cloud, of course, if the light goes through and up to the ground, it's absorbed. And so if you look at 4.3 micrometers, you have essentially a zero absorption here. You can't see anything. But if you have a high altitude cloud, suddenly at 4.26 micrometers, as it's pointed out here, you have an emission, which is a fluorescence emission here. And the size of that, of course, is only a function of the altitude. The lower the altitude, the closer to zero you are, the higher in the altitude, the higher parts you have here. So it's something which is sort of easy to understand physically, but it has been very important. And here, for example, on this, here you have a region on Mars on which you have, with a color scale which is an unusual one, in blue you have higher concentration, on red you don't have. Here you have that the coverage with the H2O clouds essentially going to the north, and so here it's dry, and then you have a huge cloud, H2O cloud collection here arriving. And now on the same spot, if you look at in the visible and at these resonant things, you have these small spots here, and these spots which are above the H2O ice, actually, clouds, are the CO2 clouds. They are very small, very localized in space and time, and that's very important for many reasons that I will just not elude it here. Here you can see both the clouds, the 2 points here, and here, and the shadows that you can see here. And if you go in another wavelength, you only see the shadows and not the clouds because you only see the ground, and you have no access to the resonant fluorescence here. So just to say that this is something which has been worked now systematically on Mars Express, not only by Omega, but also by PFS, by SPICAM and HRSC. And the advantage of HRSC that looking at the different channels, you look at different directions here, as seen here, the different channels view during different directions in space, which means that as a function of time, you will go over the same area, and just playing with that, as seen here, you can both know the altitude, of course, and also the velocity of the clouds if they move. And actually here you see that the blue and the red, which correspond to different wavelengths here, are not superimposed just because by the time they have been viewed, 10 seconds between they have moved. So there is a possibility by this measurement to have access to the entire atmospheric circulation. But more than that, what is very important that, and you have other examples here, but I will go very brief, the fact that they're located in very specific spots, and not only where the CO2 condenses, shows that the nucleation of these clouds is not merely a connection between thermodynamics and circulation. You have also the question of the nucleation site there. And it's still an open question to know what are the nucleation sites on which the CO2 are present and condensed, really. And we are now, I think, and I hope, close to the point that we'll know really what the physics of the cloud nucleation is on Mars, and that, of course, has a lot of different outcomes of major importance for the Earth also. Second point I would like to tell is the question of this planet being dead or not. You know that given the size, we are very lucky in a sense, because not only we can see all the steps of evolution, but Mars has gone through all these steps until the death, really, because Mars just died. But it's died geologically, essentially because, as well known by the HRSC counting, if you see the caldera here, the colors by here just correspond to different outflows of different ages here, and you see that the ages for this one, which is Olympus, typically range from 100 to a few 100 million years. If you do the same for all the others, you have the same sort of things here, and you see that the volcanic activity has gone from billion years to only a few tenths of million years, and you still have preserved the different outflows, which is important. It means that actually that the volcanic activity through the volcanoes was not so intense to raise the previous record. So if you do that systematically, you see that on Mars, the latest outflows are dated typically a few tenths of million years. A few tenths of million years mean that essentially it's contemporary, but we are almost convinced now that there won't be any in the future. So really, as far as the outflows are concerned, this planet is dead. And again, we have a way to know that. But that means that the outgassing is finished. And if I put this outgassing here, it's because, as you know, the question of the methane is so sensitive now that the people are planning a mission just for that in 2016. The point I would like to say here is as follows. We have the capability with the near-infrared to know what the composition of the ice are. And if you, this is the northern cap at summer when all the frost, the CO2 frost has disappeared, and actually the map here shows that when the perennial ice is only water-rich here. But the question was, and that's a work by Yves in our lab, the question was, okay, what is black here? What's the composition of that? And it happened, and we discovered that a few years ago, that, and it's in false color here, represented here, that these dark dunes, which are really dark and don't really make the difference between these and any other substrate, are made of gypsum, calcium sulfates with 2H2O. And the reason why it's in here, and that's been well monitored now, it might be, and that's really not, that has to be confirmed. That's just something that I put here. I like for you to understand that it's a possibility, and I think an amazing, interesting possibility, that if there is some gypsum here, it's just because we are at the top of the last venting of this planet here, and the planet is still venting, and it's venting essentially sulfur-rich compounds, and the reason why we have gypsum is essentially because these sulfur-rich compounds immediately react with ice and the basaltic material to convert into gypsum here. And so the dunes would just translate that process, which means that essentially this atmosphere will still be outgassing, and of course not only the sulfur-rich, but also the CO2 and N2 might be recycled from deep reservoir even now. So the 10 millibars now we have is still the recycling and no more than that. And again, instead of having this model that the people use essentially to say that you have a steady loss of the atmosphere among the time and the pressure just decreased, more likely we had, and I will go back to that, of course, an early loss of the atmosphere, very early in the process, very early, and I will tell when we think it might have happened. And then it's essentially constant over the time. So the 10 millibars might be a representative of what this planet have for billions of years, and not only for a few years, I would say. And so MSL should be able to tell us whether or not that's the case, because the fractionation would be different depending on the time out of which it's been lost and escaped in space. Of course, the MAVEN mission in 2013 will be key to understand whether or not we still have venting and what are the escape processes. And I would suggest that the 2013 and 16 mission would also and concentrate not really on the C-rich molecules but on the S-rich molecule, because if there is venting, the likelihood is not that we have most methane and alcohol, but essentially S-rich things, and that would tell us whether or not we still have an outgassed planet. So the question is, supposedly we have that, where has the atmosphere gone now, and when did that happen? And this is what I will try to tell now. First of all, if we want to know where the atmosphere has gone, let's see to the major component, the CO2. And the question was, is the CO2 blocked into ice or carbonates? As for ice, we went to the southern cap because we knew that the southern cap was thought of being made of CO2, and actually that's an optical image by HRSC of the south cap, and again what is bright is ice, but of course that doesn't tell you about the composition of the ice. This is an enlargement of these places, and that's the HRSC again picture of this bright ice here. And when you do the same with omega, taking only the photons absorbed by a given component, here you have the CO2 rich places, and the blue means a lot and the red means not at all. You see that there is a one-to-one correlation between the CO2 here and the bright places here. What is bright is essentially CO2. So omega confirmed that the cover that you see is essentially CO2. But now if you do the same with H2O, you see that actually there is H2O in the CO2, but a lot of these, for example, this point here or these plumes here are only H2O and not CO2. So all this is H2O. And actually the fact that it's green here and not red means that the entire glacier on which the CO2 is an H2O-rich glacier and not a CO2-rich glacier. And when you do the same at higher resolution, that's the visible image by HRC, and when omega looks at that, then you see all this bright is CO2, but all the rest is H2O actually. And the same here at higher resolution, you have CO2 here, but all this is water, and the same here. So in other words, if you make the 3D pictures of that, you see that the CO2 is only a very small veneer, only a few meters in depth, and no more than that. It does not account for more than a few % of the present atmosphere, which is total of less than 1 millibar. So the model we have now for the polar cap is that the CO2 is only a few meters here on the top. It does not really represent any consistent level of the present CO2 inventory, but the water is kilometer size, exactly the same in the south and in the north. So we understand that H2 is essentially blocked now in polar caps, like the equivalent of maybe 10 or 20 meters equivalent, no more than that, but the CO2 is not present as ice. Now the question is, do we have carbonates? And the fact that we don't have ice, the question has already raised that the CO2 has disappeared on Mars as it did on the Earth. At the place water was present, it dissolved and then precipitated into carbonates. So it's years since we have tried to find the carbonates. And do we have that? And essentially, to be brief also, I will say that no. We don't have large fields of carbonates. Here or there are some carbonates, and there are good reasons for that. But most of the CO2 have not been transformed into carbonates. In terms of the global reservoir, the carbonates do not count really in the process. So it goes with the fact that the N2 over CO2 ratio is so similar, 3%, that the one we have on Venus, means that both species have been lost by the same huge factor, which is 10 to the 4 maybe, with exactly the same efficiency. So that demonstrates that N2 and CO2 could not be trapped by two different mechanisms, CO2 into carbonates and N2 another process, because as you know, N2 cannot form nitrates easily. So it means that the two probably have been lost by an escape process. And the question, of course, is when. And if you want to know when, the other possibility is to go now to something entirely different, which is what are the minerals that require stable liquid water to be present? Because now the good record is no longer the feature that you will see, but the mineral themselves. The minerals will tell you really the aqueous history. And so now I will go to this aqueous history. Minerals are really the possibility to go back to the history because they give, as I say, the enabling processes and environment. To make a mineral, you need something which is readily observed and understood in the mineral themselves. The first question that we asked ourselves is, do we still have pristine material that dates the formation of the crust itself? Because everyone knows that half of Mars is still heavily cratered here. When you take an enlargement of that, and if you don't put any caption here, you don't know whether it comes from Mars or the Moon or an asteroid or whatever. It's from Mars. There is a very subtle differences, but no one will understand that. But it's not because it's heavily cratered that the material has not been altered. And the question, of course, is, has it been processed or not? So we wanted to know whether or not this pristine material has kept its original composition. And so that's the same here. And the very first map that we did, it has been improved over the time in the mafic maps. Here you have the pyroxene. We can do the same for all the mafics here. And when you see that there is a one-to-one correlation between the composition of the crust and the composition of the mafics. Essentially, the crust has still preserved its mafic composition. So the message here is that if you want to find a place which dates more than 4 billion years, which is so contemporary to the time, at least on the Earth, life emerged, they are still present there and altered, well preserved, and that's, well, the rest of the story will tell you why we have to go there, because probably we have kept all the records of what happened at these times. Now, of course, it's not to say that there has not been alteration on Mars. And when you see this map, the one I just showed, there is a lot of black stuff here. Of course, all the places, even where you have the black material there, if it's black, it means that you don't have the signatures of the pyroxene, the olivine, or whatever it is. It doesn't mean it's not made of that. Of course, it's all magmatic in origin. If you don't see that at the surface, it's just because the surface has been altered. And the question is, by what it has been altered? And when you see the correlation with the albedo, of course, what is black over there, what is altered, is what is red. So that's where the question was, is the red stuff the alteration by water or not? So the first question is it rust? Has it been transformed into ferric oxide? And this map here, answer yes. Yeah, this is the well-known thanks to Dick Morris, the hematite, the nanophase hematite, which is the small nanophase grains, which are red, really, when you see them, alpha Fe2O3. And these map here tell you that really there is a one-to-one correlation between the red material, the red soil, and the nanophase. And so, and that the anti-correlation here with this map is really very striking, right? So obviously, half of Mars has preserved its composition, half has not, and has been rusted. I will go to that, but we know now that, as was thought for a long time, if it's red, it's rusted. The question then is, has it been done by water, as the people thought? And this is where near-infrared is very, very powerful, because if you have either OH or H2O somewhere either in frost or absorbed or whatever, in what format it is, you can't hide it. You can't not allow our instrument to see that there has been water somewhere. So this is one of the first maps that we performed and procured. All the small dots here are the place in which we see hydrated minerals. And the very first thing that you see that, first of all, the volcanic material are not hydrated. And that's something that has not been outlined as it should have been, I think, in the past, because it's very fundamental to consider that the magma that went out from the crust time until the volcanic outflows are essentially dry. And that has to do probably with the very early process by which the impact that impacted Mars very early, and I will go back to that, which has very likely happened at the same time an impact went on the Earth, out of which the Moon formed. Most of the water was released at that time, and just because Mars was too small, most of this water could not come back to that, and the magma has not hydrated there, and that's probably a reason why we didn't have plate tectonics starting at that time, although we had that on the Earth for the same reason that the water could enter the magma on the Earth and not on Mars. The second is that the bright dust that you see up there, which is in the black stuff here, is exactly not hydrous. So there is not a single droplet of water there. Again, when you get rid of the frost, of course. In the material itself, you don't have that. And it means that essentially these ferric oxides are not hydrous. It's anhydrous things. So they have not been made like goethite would have been by liquid water altering the rocks on the magma. The alteration is probably an atmospheric alteration by the H2O2. You know, the H2O2 has been found to very, very low abundances, a few ppb, no more than that. That's sufficient to alter the surface, but it requires huge timescales, billions of years, and it only affects a fraction of a millimeter. And this is why you see any gardening will put on the surface pristine material, and that's why you see the track of the rovers. It's just because the alteration layer is so thin. Now, the ancient syllogism from red, if it's red, it's rough, if it's red, it's water, if there is water, it's life, on which most of the people live until the space age, actually, that just vanishes. So now, it's not because we didn't see this mineral that there is not others, and the question is, okay, what are the other minerals which appear in spots? And the first thing that we can say, of course, there are sulfates, and I will not be long on the sulfates. We discovered the sulfates from space at the same time. Opportunity found these, which is only March, April, in 2004, after he landed. We discovered that also, and there is, these sulfates are spread over not the entire crust, in a few places, and I will elaborate a little bit why it's in these places and not elsewhere. We have only, it's not widespread, you have a few places in which we have the sulfates, and I will explain to that later. But the important thing is not really the sulfates for the story I want to tell, and I will explain to you in a minute why. The real important thing, I think, the discovery that really changed our life, was the fact that we found these hydrated phyllosilicates. Phyllosilicates it's a family of silicates in which the clays appear. We don't say clay because clay means a powder thing, so we're not claiming that it's powdered, it's maybe this really phyllosilicates. But that, I think, is a very important thing, and that's the work that François Poulin and others led in our institute, and of course CRISM has completed that. So when you see all the things, you have a huge variety of phyllosilicates. I'm not going to expand on that. The different things tell something on the way these phyllosilicates have been formed. But again, when we found that, I mean, it took a year or so for us to confirm that what we found was dry. We found that in the early 04, just after we arrived, actually. We did not publish that until the end of 05, because we knew that it was so important. We absolutely wanted to be sure that what we found was that. And so I remember that at the COSPAR meeting, there were so many countries, I wanted everyone to understand what clays meant in terms of the importance, and that's why we did that. So, the reason why the phyllosilicates are so important, I think, is that among the entire families of rocks, the altered rock that we have found, these are really the ones that require, although undoubtedly, although there is always a possibility it's not true, long-standing bodies of water. We need leaching a lot of times basaltic material with water, and that's really very specific to these rocks. Even the sulfates do not require that. Sulfates can really precipitate when the water evaporates immediately, and you have a lot of, even the carbonates do so. We have not found carbonates, but carbonate does not even mean that necessarily you have long-standing bodies of water, and the same for sulfates. Phyllosilicates, up to now, we have not been able to find any possibility to form that, except that having stable liquid water over a long period of time. So the question is, are we sure or not of that? And second, if that's the case, the phyllosilicates will trace the only possibility for Mars to have harbored stable liquid water over long durations. Again, when you want to know at what time that might have happened, the question is, where have we found them? And the phyllosilicates are found, as you saw, in all around the crust, but only but all around the crust. It's in the heavily cratered places here. And this is why we have this now, this emphasis that this crust is so important, because it has kept the record of these early times, and these times were the time during which water was probably present. There is only one big site on which we have found the phyllosilicates, and it's exemplary. That's why I'm trying to, once again, to show that. This is the Mars Valleys, which is very close to the Ares Valleys on which Pathfinder landed. And the HRSC people always put blue when they should not, because, okay, of course, that tells that there has been water and then an ocean there. When we go with the real colors as seen by Omega, there is no blue at all here, because there is no hydrogen minerals in the channels and in these, how do you call that, where the channel goes in what might have been an ocean here, which is not at all the case right here. But in all the white things here, we have found phyllosilicates here when no one expected there would be. And the reason why, again, is because the outflow channels have been created after the time during which water was present and made these phyllosilicates here. When it did that, at the time the outflow channels were made, the water was not stable anymore, very likely, at the surface. And at the same time, it eroded massively these terrains. It evaporated or it percolated, but it could not sustain long body of water here. And that's why we couldn't find any signature of hydrogen mineral there. And so that's what we said. Most of the phyllosilicates, at least, predate the outflows. And we'll go to that here. So the fact that these have been made during the bombardment, I will finish by that, of course, is absolutely fundamental in the story here. So that the molar topography here, that's the place where we have lava outflows, and actually this is the volcanic outflows as seen by the high calcium pyroxenes, which is easily identified. And this is where you find the phyllosilicates, exactly in opposition to that, in the higher terrains, heavily cratered, and not in the lava plains here, which, by the way, are again totally dry. So that's where I think the people should go now in the future, and that's what we have said. And this is the molar map here, and all the circles here are the landing site for MSL that we have proposed. And now we have one of them which have been suggested, and this is the remaining one out of these four here in which MSL might land, because that's a very important and interesting thing. So again, these are the places in blue where we have the trace that water might have been present in the past. Again, if I have time, I will explain to you why it's not on its spots and not entirely blue here, but there are good reasons for that. And that's where I hope we land, and that's the place where I would like MSL and possibly ExoMars, if by tomorrow the Council of ESA finally decide on that, and we'll know that tomorrow evening. I hope this mission will take the place. So if there has been phyllosilicates, it's at the time where water was present, and that's the only time during which it happened. So again, if water was stable, it's during this heavy bombardment, and I will go to that. The sulfates form afterwards, because it's formed after Tarsis formed. Tarsis formed after the end of the bombardment. It's not cratered at all. And the reason why we had to wait for Tarsis to be there is for two reasons. First of all, you see that the sulfates are found in context coupled to Tarsis. And second, essentially because you need sulfur, and the sulfur really comes from the outgassing that was coupled to the Tarsis building. So that's why we issued this new map of the history with the times labeled by the name of the altered material, which is the phyllosilicates here, the sulfates here, and the ferric oxide here. There's the Greek names here of this period of time. And again, if there has been habitability, it's much earlier than that. It happened that none of the landers or rovers ever went there. They all went in these areas and never there. That's why we instead go Phyllosian now on all the T-shirts that, as you remember, were plotted here. We sold them, now we gave them here. And I knew that Jim would not come here, so I dare to say that he was septic at the beginning, but finally his wife helped, because Anne understood finally here, and okay, you can read it, okay. But that's important. So the last point is, okay, something happened here. I will take some minutes to try to emphasize what happened here. Mars had a global climatic change at that time, and the Earth didn't have it. And the atmosphere went to a dense atmosphere to a much tenuous one. That's probably the time at which it drops in pressure. It went to alkaline, neutral alkaline, to acidic very highly, and that's seen in the mineral themselves, because again, the phyllosilicates require a neutral environment while the sulfates require a highly acidic environment here. And that's what we call the PT boundary, the Phyllosian-Antiochian boundary, which is as important as the KT boundary. And the question, of course, is why did we have that on Mars and not on the Earth? What was the driver of that? Is it the volcanic activity? And the answer is no. The volcanic activity was started really by the Tarsis building, and that went late in the process. Tarsis and the filling of the northern plains were done after the heavy bombardment had ceased, as obvious by the crater counting that we have here. And so that's why the sulfates went much later here, but of course that happened after the bombardment had ceased. So that's the reason why this picture was still on many of the walls of NASA buildings here. is fundamentally wrong, I think, and we have to change our mind of that. It's not possible that we had stable oceans at the time the volcanoes were there already. At the time we had tar seas on the volcanoes, the atmosphere has gone, and we were below the triple point. It was not possible at that time to sustain a stable ocean there. So this picture was fundamentally wrong, I think, and that's not amazing. I mean, if all the things that landed in this blue part for good reason at that time failed finding any sedimentary rock for that reason, I think. So what else? What dynamo drop? I think this, again, although it's not confirmed, I think it's one of the most promising tracks to see. The dynamo dropped, I think, exactly there, and that's what ended really the era during which water was stable. Again, most of the answer is given here in something which has been printed some years ago already. Important thing here is that, okay, all the colors here refer to the remnant magnetization here. And the important thing that you don't have remnant magnetization in Tarsis and in the big basins here. What does that mean? Essentially, it means that Tarsis, the filling of the northern plains and the big impacts here essentially went at the time the dynamo had stopped. If not, that would have gone also when it went crystallizing and solidifying among the Curie point. It would have also get some remnant magnetization. So at the time this impact formed, and the impact again were during the late impact bombardment times, the dynamo had vanished already at that time, but not during the crust solidification. So there has been really a cutoff in time during which, before that, we had a dynamo, after that we didn't have that. We consider that very likely this dynamo drop had a big impact on the evolution of Mars. Again, that's something for which the next missions will study that and confirm, probably, but the idea that without a dense magnetic shield against what we call the young sun, but the young sun is not a sun during the first million years, it's during the first 100 million years. When you see the variation of the solar wind intensity, of all the parameters, the X, remember that the young sun was in a huge, intense X-ray emitter that ionized all the atmospheres of the planets. If you were not protected against the solar wind interaction with the ionized atmosphere, you were sputtered away very rapidly. You could have bars in much less than a few tenths of million years. So if you were not shielded, essentially your atmosphere had to leave. And that's probably what happened here. Before that, you had a shield, and you could sustain greenhouse gases to maintain liquid water above the triple point. At that point here, the greenhouse gases faded out. They escaped, they were lost by the planet. Immediately the water percolated or evaporated and was just thrown away. And the remaining water that percolated into permafrost, at the time Tarsis went here, the rays of the geothermal front brought all this water as huge supply of water to the surface. They cemented the sulfur that was brought by the outgassing, and that's why you have these sulfates close to the geothermal front points. But again, at the time this water went to the surface, the pressure was too low to maintain liquid water as stable, long-standing bodies of water. So that's why you don't have necessarily long-standing bodies of water associated with sulfates, and certainly no with the outflows, because the outflows, again, were these violent supply of water at the surface. At the time, the pressure was too low, probably, because, again, that happened much after the dynamo had stopped. Why is that on Mars and not on the Earth? You don't need to read that. I think the sole idea to be checked is that the size of Mars is sufficient to explain. If you don't have enough radioactive radiator there to maintain convection in the mantle, you will not be able to maintain the convection in the core, because you need a lot of energy to be extracted from the core by the convection in the mantle. If the mantle convection is not sufficiently sustained, then the core convection will drop and the magnetic field with that. So I think that the core idea there that you need to have sufficient radioactive species in the mantle to maintain the magnetic field, actually. And that's what happened on Mars, the drop, and not on the Earth, because it was large enough to have enough radioactive things here. So did we have extension of life at that time? In other words, if we had similar Earth and Mars at the beginning, did we have the divergent pathways after life emerge on Mars or not? And that will be my few concluding remarks here. Was Mars ever habitable? These are compare the history of the Earth and Mars as it was proposed in the old times, which is up to a few years ago, both for the Earth and Mars. And again, that's the time of the heavy bombardment, essentially. And that's hell had in its, I mean, that's per definition, because Hades is really the god of hell, right? Which means here you have paradise, right? So that's heaven. And that's why, essentially, the people consider that Archean start here because, essentially, you don't have a record earlier than that, and also because, again, you can't have anything really livable here. Habitability had to start here because the impacts were always considered like sterilizers. I think I will challenge that because I think it's basically wrong. Actually, these maps that we have on our wall here say exactly the same, that we had, again, water after the volcanoes had been put in place, so after the bombardment ceased. And I think that that's also wrong. So both for Mars and the Earth, we have good reason to change. And it was thought by these and these that this was prebiotic. The life had to start afterwards. I think that now we have good reason to consider that for both Mars and the Earth, things happened much earlier. On the Earth, and I have no time, of course, to discuss that, but that's very important. That's really recent measurements made only a few years ago. You know that we have this very old zircon which have been found as detritic material in both Canada and Western Australia, and in thing that they have inclusion, uranium-rich inclusion, which have been able, enabled to date them, and they are all more than 4.1 billion years, maybe 4.2, 4.3, and the oxygen-16-18 ratio there tells that this zircon had been made in a rock which was in contact with warm water. So we think that this zircon, actually the granite in which the zircon were formed, we have lost the rocks, of course, because they have been destroyed, but the zircon is so stable that we only have the zircon. The zircon were in rocks that probably were formed at a time the crust was still hot in contact with an ocean. That's the only measurement that would say that we had an ocean on the Earth very early, maybe 4.2, 4.3 billion years ago, soon after the Earth condensed here. So the Earth's habitability probably has to be shifted from here to there, because if we had an ocean, why not? And so the question, of course, is, can this water here survive the end of the bombardment or not? And the answer is yes, if the bombardment actually went not steadily like that and so on, but made in two things, what I call the early heavy bombardment and the late heavy bombardment. And as you know, and many others than me in the room here could argue more than I would do, but I think there's a very good argument that actually that's the way the bombardment operates in the solar system everywhere, including, of course, on Mars, on the Earth, and everywhere. The reason why, again, it has to do with resonance when Saturn went exactly 2 times farther away than Jupiter, and so this resonance excited transition from the outer solar system back to the inner. And you need something like 500 million years to make that happen. So that's very likely, really. And if that happened, it has been shown that, in that case, this bombardment, of course, we don't know exactly what it was on the Earth, but when you extrapolate what we see elsewhere, which is essentially on Mars and on the Moon, you compute what was the intensity of this bombardment here on the Earth, and you are led with this idea that this bombardment did not evaporate more than 10-15% of the oceans. So more than 80% of the oceans survived here. That's why I put the blue all around here. So you had not this, but this, really. So probably this heavy bombardment here, which had a lot of trouble for many things, did not put the oceans back to the air. The ocean survived here. So the Archean starting here, if the Earth was habitable here, it might have been continuously habitable. And the question then, whether or not life started, has to do with the way the carbon-rich species might have happened here. It could be by the impact from micrometeorites, as you know, or by the ocean floor, by this volcanic activity. Both are feasible. If it goes down there, it could have been from serpentination. And if I put that, it's just because the methane questions, of course, is very sensitive now, and we know that interaction with the ocean and the crust would make a lot of CH4 and NH3. That's possible. But the important thing is that if the Earth was inhabited here, it might have been inhabited here too. Because if it started here, because we know that, because we have some record here, why should not be started here? Again, what does it mean to be habitable if it's not inhabited? If it's habitable, there is life. If it's not inhabited, it's because it was not habitable, right, essentially. So the question whether or not it's in here, I say there is no reason why on Mars, on the Earth, we will find the answer, because there is no record at all of this period of time. On Mars, we have. And that's what I'm trying to say now. At the time, the zircon are the tracer here, we had the Phyllosilicates over there. And essentially, the Phyllosilicates and the zircon tells the same sort of story, except that the Phyllosilicates tell more, because that's really the entire rock that we have here, and not only the residual things after the detritus that the zircon would be. We have the entire rocks here. And in this terrain that I showed, if we land there, if we look, we have the entire environment present for study here, for screenity. So the question, of course, is, was Mars habitable as the Earth was? We don't know the answer, but we know that now if we go there, during this decade, I think, we will know that. Now, if life on the Earth started here, it would have started here too. How do you manage to go from here to there? Because we know now that the oceans disappear here because the dynamo stopped probably. So how will you survive here? And that's really the problem. If life started after the LHB, it's hard to conceive that life will be present on Mars. But if life started here on the Earth, then it might have started also here. The question of what happened afterwards here is not trivial, of course, whether it will go dormant or whether there will be later input of water that make this mode dormant to survive up to now. Maybe yes. But what is really new, that we know now that Mars will tell us that. Because if we go there, that will be a unique place in the solar system that has preserved all the conditions during which probably life appeared on the Earth. So that's what I'm saying here. Thanks to the Phyllosilicates, Mars is really unique to offer the possibility to study the time during which life started anywhere. And let's go now one step closer to the beginning. Let's go to the early bombardment phase here. We know that here we had a big impact on the Earth. We have not finished to evaluate all the outcome of this impact. It's tremendous. Most of the atmosphere are left. If not, it would be Venus-like, and we wouldn't be here to discuss that. Most of the volatiles went to the accretion disk, but then because the Earth was sufficiently thick and massive, most of the water went back there, and because the moon formed, the tides on the moon maintain such high temperature magma that most of the water could enter the magma, and so the plate tectonic could start, which didn't happen on Mars. But are we sure that Mars was not impacted? And actually there are many reasons why we think that Mars has been impacted also. Are we sure that the moons we have now, Phobos and Deimos, are not formed by this impact? Personally, I'm almost convinced that the answer is yes, it's been formed there. As many others in the room here, I said long ago that because of the composition of these moons, they are captured asteroids. It's just stupid. First of all, because it's impossible to capture an asteroid, essentially. You have to release the energy somewhere. And if you tune the parameters for that to happen once, you will not do that 2 times for 2 different bodies, which is Phobos and Deimos. That's one thing. The second is that it's not because it's not differentiated that it doesn't come from Mars. If you have an impact on Mars, you volatilize all the material, so you have a high temperature gas in a disk, out of which you will recrystallize a body, and the question of whether or not this body will be differentiated has nothing to do with the composition out of which it's formed. It's just a matter of how much energy you will have stored here to redifferentiate it. And if it's too small, it will remain as it is. So, very likely, Phobos is just Mars-made and undifferentiated. If we go to Phobos, and as the Russians will do with the Phobos Grand mission, we have a splendid mission because for the first time we'll demonstrate that possibly there has been an impact on Mars, and maybe the dichotomy is the result of that because the geometry was such that it was not completely fused and rebalanced afterwards, and Phobos and Deimos will tell us that. With Phobos Grund, there will be Institut measurement in which we will also demonstrate locally, even if we don't have the written samples, whether or not it's accreted at 1.5 or 3 AU. If it's at 3 AU, there will be water and carbon-rich species. If it's at 1.5 AU, we won't have water in the material themselves. So that will be dramatic to measure that, and we'll do that actually in 2 years. So Phobos, and that's a pretty picture of Phobos made by Mars Express at Orsay, will tell us that. Phobos will tell us whether or not there has been an important accretion history all over in the solar system, that we have lost the record essentially except for the moon, but looking at what happened on Mars, it will tell us the probability that it happened elsewhere with different geometry, and of course for the question of survival, it's sort of fundamental. What I'm saying here that really 30 years after the Viking, it's remarkable that although the Vikings sort of demonstrate that Mars is essentially an arid system with no life at all for obvious reasons. The question for Mars to have harbored conditions during which water might have been stable over long duration is reinvigorated. We can revisit that now, and the thing that we know where to go. And we are not going to decide where to go by the simple images, because the images are very misleading in the sense that you can make structures, fluid structures, without water to be stable, as we have by floating on the Earth actually also. The composition is the key now, and I think that what has been done by these Mars Express and our mission is fundamental in this respect. I say here, exobiology is really now entering the real science era now. It's really now the scientific era, because we can have an approach which is not only thoughts or whatever. We can make prediction, make measurements, and that's what MSL, ExoMars, and then the future mission will do. So that's why I hope that finally ExoMars and MSL will be the Phyllosilicates rover that we dream of, and will land where we hoped they will. And possibly the 16 will be 18, that will go. That will pave the way to the sample return, of course. But I will finish by a few words on the way all this venture has been conducted over the times. It has been initiated, frankly, and I dare to say that here in that room, that really ISM Phobos 20 years ago, it was launched in '88, and it was operating in '89. It was the first ever imaging spectrometer built by a consortium made by our institute at that time. And it's out of that what we propose Omega on the Soviet mission that was supposed to fly in '92, postponed in '94 and '96. But something interesting happened in '88, and I will just take a minute for you to remind you what happened. '88, Russia was still Soviet Union, and there has been for a long time cooperation between France and Soviet Union starting in the '60s. But suddenly, by the end of '88, NASA decided that it might be a good idea also to cooperate with these people, because they had a lot of things. And so they sent the first, and it has been the first bilateral NASA, whoever their EKI meeting. It was by the end of '88. And the people from here went there and they said, okay, you are flying in '82, mission to Mars. We'll provide for you the infrared spectrometer, VIMS. And the Russians said, no, we have one. It's Omega, so we don't need it. And they were really very, how can you refuse this offer? No, that's the way it is. We have an instrument. But if you want, just contact them. And so I didn't know anyone there, but okay, we had a phone call and then a fax, because we had fax at that time, no internet. And I've been invited to NASA and said, well, we didn't know how many people would go, so we were 4 from France. 2 engineers, 2 scientists. And there were 50 people in the room. Some of them were being here. Now it's essentially a good friend of us. And actually, I have a meeting, a fraction of that here. And that was amazing, because the NASA thought that it would be a half-a-day meeting. And actually, after a while, I saw a paper circulating in the room, who is going to stay overnight, because obviously the meeting will be a little longer. And the idea that they said, okay, we are flying with the Soviets to Mars. Are you willing to work with us? And I say, no, I'm sorry. We have an instrument. If you are interested, we can discuss. And so the day after, we had on the blackboard, which is here, 4 missions divided into different lines here. There were the 4 missions were Kraft, Cassini, Mars, and Vesta. Mars and Vesta were supposedly French-led for the infrared spectrometer, and Cassini and Kraft would have been NASA-led, but that would be a single instrument, and that's how started the Omega VIMS venture. Unfortunately, and okay, you recognize Larry Soderblom, Terence Johnson. A few months later, 2 years later, without any phone call, NASA withdrew. And they thought that because they were responsible for all the focal planes, we would have made all the spectrometer, they would have made all the focal planes, they thought that we would not recover. But of course, we had asked NAS to support us to have a backup solution just in case. And so we had focal plane, INSB, and they fly now on Mars Express, because the instrument which is flying now is that one, the one we prepared. NASA decided not to go. That's very unfortunate, really, because we kept very good friends there, but they were not on Mars, and we had to wait another 15 years for CRISM to be there. And Omega was really fruitful, right? But VIMS went. Kraft was cancelled, but Cassini was there. And although NASA decided not to go on Mars, we decided to stay on VIMS. And so we are still on VIMS, and it's good cooperation. So the Omega cooperation on VIMS is still present. We built some of the hardware has been made by us, and we are very... The problem, of course, with NASA, that even if you give only a finger there, they will say NASA takes Omega on Mars, which of course is not true. And out of that, I must say that all the Virtus instruments that some of you might know on Rosetta, Venus, Dawn, and many others actually are made also from that, because we decided to expand the concept to our Italian colleagues, and now really there is a huge branch of such infrared spectrometers that are flying now. ISM was made at the time. We had two students, which are, one of them is in the room here at Brown University, and they started to work with us on ISM at that time. And these people now have grown 20 years later, and they are responsible for the Caribbean instrument. So that's also the way we build this cooperation on the long term, trying to have links which are really sustained over the times. So now we are working on Micromega, which is the miniaturization of Omega to make an infrared microscope that will be able to tell you grain per grain the composition of what you see. Whether it's ice or minerals, hydrated, whatever, you will see that. And more than that, if there is around some grains, for example, some carbon-rich materials just growing, you will see that. So Micromega will be the first to be on board the Phobos Grunt and hopefully on ExoMars, and then on the equivalent rover of NASA, if ever. That will be the possibility to discriminate whether or not we had something like biorelics there, obvious. So mass exploration, bridging past and future, it is the way we do that for the teams. It is a possibility to read on Mars the old times and the future of the Earth. What else? I didn't make a picture. I mean, Clooney was with Omega there for whatever other reason, but still, we like it. And I will finish by that, which is really the way we try to combine the past and the future. It's maybe one of the pictures I'm the most proud of. A year ago, I mean, we have several times meetings, of course, and a year ago we have these Omega meetings, which was made only by the young students which had made their PhD on data collected by Omega. We had a little more than 20, well, more than 25 now, and that's really the way we try to build the generation that will able in the future to understand how planets behave. You have 7 countries here represented. They are all friends among each other. They are really now a joint team for the future. Thank you.
Excellent talk. Do you want me to moderate questions? Or do you
Sure, if you like.
We have time for some questions. Yes, right in the middle.
Is it possible that the mesospheric clouds can nucleate around meteor dust like
I'm not sure. You said are nucleated around what? Meteor dust? Okay, first of all, we don't know. It's obvious that they nucleate around very small grains. We think so, not ions, as it might be on the Earth. It's probably not cosmic rays and ions, because that would not be localized. If we see the cloud so localized, it has to go also from a very specific circulation pattern here. Convection will bring the nucleation sites in region where, of course, the CO2 can condense for thermodynamics. Which grains are there? We don't know for sure. The SPICAM UV spectrometer shows that we have a family of very small grains over there, which is a few tenths of nanometers in size. Of course, we don't have access to the composition. My guess, but for the moment it's just a guess, and I can say that here, although it's not published yet, that it's magnetite. I think that the smallest grains we have in the air now on Mars are very tiny magnetite grains, maybe 10, 15, 20 micrometers, and that's maybe the seeds on top of them on which the CO2 nucleates. The reason why I'm saying that is, as you know, the magnet on the 2 rovers collect all the grain there, and even if you have an olivine grains or a feldspar or whatever, they have magnetite on because they are magnetic. And I think that these grains circulate everywhere. As you saw, the ferric oxide, the nanophase, does not circulate very far from the place they are being found or made. That's why the The old craters places are not red yet. In 2 billion years they will be, but not now, because they have not been oxidized yet. The grain, these ferric oxides do not circulate. I get that the magnetites, which are made probably by the same process, are small enough to go to very high altitudes, and there is some upwelling beam that will make these sites very favorable for nucleation. And that's why we see them over Meridian in particular, 0, in latitude and longitude is a favored place, and we see that operating continuously.
Right there, is that Jerry Schubert?
Yeah, if Mars convection, declined so as to turn off the dynamo, how would you get forces forming afterwards?
Okay. Okay, I can only translate what I think I have understood from colleagues which are in the room, actually. The idea that it's not because the convection stopped that the mantle stop activity. You will have downwelling plumes in any case from the mantle. The cold plumes will go to the interface, to the instability layer at the interface between the core and the mantle. And that will finally lead to upwelling plumes, probably what you call degree 0. I mean, just Tarsis is just one, so you have just one single plume going out. The modeling is not finished, I must confess, but that would be the place where to do so. So it's not because the convection, the global convection is out, that you don't have movement in the mantle that will not make Tarsis to go. But the important thing is that for these plumes, upwelling plumes to come and make Tarsis, whether it comes from the interface with the mantle, core mantle or at high altitude, I have no idea, but it takes tens of million years. So when Tarsis forms, it's a long time since the dynamo had stopped, and that's why the sulfur-rich outgassed material will, first of all, spread over the entire planet, and that's why we have sulfur everywhere on Mars, on the regoliths, but not sulfates. Sulfur, we don't know in which format, actually, because it's just spread out there. And the reason why it's a dominant species, essentially, because everything else has disappeared there. But the sulfur there will probably be transformed and oxidized at the same time it's outgassed and go back as an acidic material, because it will immediately, whether it's H2S or FAS even before, it will go into SO3 and finally H2SO4 when it comes back to the surface. On voit rien ici.
Okay, well, thank you again, Jean-Pierre, for an incredible
very
talk.
much. Thank you very much.
Congratulations. Thank you. And that closes the session.